Okay, next we are going to solve the example problem number 40. It's on page 361. So we're going to put what we learned in this problem. Okay, a ball with a radius r and mass m is released down a track. The total elevation change is h, and determine the speed of the ball when it reaches the bottom if we ignore rolling and if we include it. So given as a ball rolls down a track and we're trying to find the final velocity of the ball for a rolling ignored case and also for a rolling included case. Okay, so for the first part, since rolling is ignored, that means there's no grab, kind of, right? There's no friction. So it's just going to slide, but there's no friction. So there's no kinetic friction, there's no static friction, nothing. And so it's just going to be kind of a sliding case because there's no rolling. Okay, it's kind of hard to imagine this. Like if you kind of push a barrel down the hill, you'll see that it's rolling because there's friction in real life, right? But just assume that it's not rolling in the first case. And in the second case, we will have friction so that it kind of grabs the object and then kind of rotates it, right? So we will talk about that. And we'll talk about what type of friction we have in that case as well. And for both cases, there is no air drag, okay? So what we need to do here, since we are trying to find the velocity, and again, you can hopefully now see by now that from chapter 7 and 8, we've done all those energy problems. This is another conservation of energy problem, okay? Because you need the velocity that's related to the kinetic energy, and then you have the elevation, you have some rolling or not, depending on the part you are looking for, but you can kind of see some of the energy terms in the problem. So this is a symbolic problem, and we don't really have any numbers, but what we can say is that in the first part, since we are ignoring the rolling and it's gonna just kind of slide down, right? Compared to the part B where there is rolling, so that initial potential energy right now, you can see it on the figure, right? That potential, there's only potential energy because the object is not moving, not translational, not rotational, there's no motion initially. So there's pure potential energy right now. And that will be used to move the object linearly and also rotationally, right? If there is a rotation. So since part A is just rolling, ignore rolling, and it's just sliding, there's no rolling, so potential energy will be just transferred to translational kinetic energy, right? But in part B, that potential energy will be used to both rotational and translational kinetic energy. That means since translational kinetic energy is related to the speed of the or the velocity of the ball at the bottom, when there is rolling, some of the energy, initial energy, will be used for rolling as well, and it will kind of make that speed at the or velocity at the end less if there is rolling. So what we should say then, part B velocity should be less than part A velocity. Okay, that's what we can see before solving it. Okay, so solution. Without rolling, okay, that's what we need to keep in mind. We're going to apply the energy conservation. As usual, we write down the entire thing. So start from the kinetic, right, and then potential, then internal energy, then work done and heat. So we write the equation. Kinetic energy has two pieces, translational and rotational. It may, so we're just putting them. And then so is potential energy, gravitational and elastic. And internal energy also might have two pieces, right? We can also write this as delta I plus delta IF due to friction, like thermal energy. But you can keep them combined as well, as this problem solution does. And on the right side, we have the heat transfer and the work done by any forces that we'll consider using a free body diagram. Okay, so first step is to simplify this, right? Translational kinetic energy, we will keep it because we are trying to find the velocity, final velocity of the object, right? Rotational, there is no rotation, right? we are going to ignore the rolling. So that goes away. There is a change in elevation, so we keep delta UG. There is no elastic potential because there's nothing acts like spring. And delta I, again, this is frictionless part. And also, there's nothing else to change the temperature or pressure. That goes to 0 as well. There is no heat transfer. So we have only 3 terms left. And as you remember, work term, we do investigate it further because we need a free body diagram first. So this is what we have left with then. Okay, so far. Next step is to draw a free body diagram. As usual, those are the steps from chapter 7 and 8. So we are still following the same stuff. So we have, from the surface, we have the normal force. It's perpendicular to the surface, right? And there's weight force. And since there's no rolling, there's kind of no grabbing from the floor, right? There's no other forces acting on this object. So one thing I want you to kind of see is the normal force will kind of balance out with the weight force, like this component here. And this horizontal component to the surface of the weight force will accelerate the object downward, right? That, in terms of forces, it also makes sense that it's going to speed up because there is a force acting on the object. Okay, but there are only 2 forces. So if you go back to the work term and then just focus on that, you can see that normal force is not going to do work because the displacement is this direction. Let me get rid of these. And you can see that normal force and the displacement are perpendicular to each other, and the weight force is not perpendicular to displacement. However, we are already keeping delta UG, right? So we're going to say that there's no work done to put it in the equation. So we're just going to simply say work term is 0, okay? Again, because we did include it as the work done by the weight is included as the UG. Okay, so next step is kind of expand, and now we will simplify again, right? Final minus initial, final minus initial. We have 2 energy terms, very straightforward. We've done this before. We didn't specify much about rolling versus not rolling, but now we just kind of doing, this is like a earlier chapter 8 problem kind of so far. So again, we are going to simplify some of the things. Initial kinetic energy is going to be simply 0 because initially it was at rest, right? And we can also say that the bottom level, as you can see it on the figure, bottom level is y equals to 0. So we can say that the final potential energy is going to be 0. So let's do that as well. So we have only 2 terms left, and you're going to put them in there into the equation. So we got kinetic final equals to potential, gravitational potential initial. So now we're writing the definitions of those energies: 1/2 mv squared for kinetic final and mgh for potential energy, gravitational potential. So what we see here is mass will cancel out. This is very important. It's really like a beautiful equation because that means it doesn't matter what the mass of the object is, anyhow you will get this velocity from this. So if you just do this algebra, you're getting 1.414 in the root of gh. So again, as you can see, there's no mass, there's only gravitational acceleration and the height. If you release different objects, different masses from the same height, and it's again on Earth because you need g, same g, then you will get the same speed. So that may not be very intuitive because that's not what happens in real life, right? And because that like the things rotate and spin instead of frictionless surfaces most of the time. So I think that's an important part. Again, without friction, all sliding objects will reach the same speed at the bottom, regardless of their mass or shape. That's what we see from this equation. And if we didn't really do this problem symbolically, you may have skipped that part because now we can see that what it depends on, velocity depends on g and h and some constants, right? So you can see the dependence. It's really nice to solve problems in symbolically. In the next video, we are going to look into the rolling case, and we're going to repeat what we did, but it's going to be a little bit more in detail because we have some extra stuff.